Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 649, Dota2 Senates. This is a medium difficulty Leetcode problem, and the problem description tells us that in the world of Dota2, there are two parties, the Radiant and the Dire, and the Dota2 Senate consists of senators coming from these two parties, and the Senate wants to decide on a change in the Dota2 game. And each senator can exercise one of two rights. They can either ban one senator's right to make a vote or announce a victory if all the senators that are able to make a vote or have rights to vote are all from the same party. So if we only have Radiant senators left that can vote, Radiant win, or Dire if they're in the other case. We're given a string called Senate, which represents each senator's party belonging. Each senator is represented by a character R and D for Radiant and Dire respectively. And there is a round-based procedure which starts from this first senator to the last senator in the given order. So we basically, we need to suppose that every senator is smart enough and will play the best strategy for his own party and predict which party will finally announce the victory and change the Dota 2 game. The output should be Radiant or Dire. So there's a lot to take in here. I think it's best to just go straight into an example and then look at the description again. So here we're given a Senate, which is R and D. So we have R and D, and the output is Radiant. Why is it Radiant? Well, obviously, the Radiant senator will vote out D because that's the only senator he can vote out. And in the next round, the only senator remaining is the senator from Radiant, and so Radiant win. So that's basically the problem. This problem description is so long, but that's basically the problem. We have a bunch of senators, and we need to, it's a round-based procedure, and we're told here we start from the first senator to the last senator. So it means basically we're iterating from the beginning to the end of all the senators, and then allowing them to make their respective votes. And here we can see that we want to suppose that each senator is smart enough and will play the best strategy for his own party. So what does this tell us? Well, it tells us this is probably a greedy problem. This is some sort of greedy problem, right? So, what's greedy about this problem? Well, let's say we have R, D, right? This Radiant senator over here, he wants to take out a D senator. He wants to take out a Dire senator. Does he want to take out this senator, or does he want to take out this senator? Well, if he takes out this senator, that's okay. But then this Dire senator will obviously take out, if he's smart enough, he will, and we know that they are, we have to assume that they are, he'll take out this Radiant senator, and Dire will, and this is not optimal. We don't want that. We don't want the senators from Radiant or the senator from Dire to take out senators from the other party. So, instead, what the Radiant senator is going to do is he wants to take out this senator over here, so the senator closest to him. So this is kind of the greedy aspect of this. We want to take out the senators closest to us, not further away from us. So we always want to take out senators that are closest to us. Okay, so that's the problem description. Let's look through another problem, right? We have RDD. And actually, I'm going to look at how we're solving this problem. So we're going to use two queues to solve this problem. And we're going to, this is again going to be a greedy problem. So we're going to pick out the closest senator to us from the opposing party and vote them out. So the way we're going to solve this is with two queues. And we're going to compare each senator from each party, and if we vote out, or if we end up with a queue that's empty, so all the senators in a queue, in the Radiant queue have gone, for example, and the Radiant queue is empty, well, that means the Dire queue will have elements or senators left, and that means Dire wins, and the opposite is also true. So let's actually look at how we would solve RDD. So we have a radiant queue, and we have a dia queue. So, with R, we have, let's put indexes. So we're going to put index 0 is radiant, and for dia, we have indexes 1 and indexes 2. So we compare 0 and 1. So we want to compare these two senators to each other. Which one appears first? Well, the radiant senator appears first, which means this senator gets to make their first choice, right? It appears, he appears, before the dia senator. So the radiant senator gets to make the choice on who to vote out, and obviously he's smart, so he will vote out 1. So he will vote out the nearest dia senator. So we remove the dia senator and we remove the radiant senator, but wait, we don't want to actually remove the radiant senator because, our senator is still in the game, is still able to make votes, but only in the next round because they've already made their vote for this round. So we can put the senator back in, but instead of putting 0, and we want to make sure this cyclically is sound. So instead we're going to increment it by the length of a senate. So we will say, let's put 3 back in. So now we have a new index of 3, but this represents this original radiant senator. And then we compare 2 and 3. Well, which one appears first? Well, 2 is smaller, so 2 gets the first vote. So 2, the senator from dia, will say, okay, I want to vote out 3. So now we only have 1 senator remaining, and that is the senator in the dia queue, in the D queue. So the D queue is the winner. If it was if it was the other example that's over here, and R would end up being the winner because there would only be a senator in the R queue. So I hope this actually kind of makes sense. It's a bit confusing to explain, but we want to have 2 queues, and whichever queue ends up empty after we do all the logical comparisons is the queue that loses, and the queue senators inside of it is the queue that wins. So let's actually get to coding this up. So the first thing we want to do is remember that it's costly in terms of time complexity to mutate a string. So let's actually convert our Senate string into a list. We want to have 2 queues, a dia queue, and we have 2 decks, one for the dia and one for the radiant. So another deck. And we want to populate these queues initially. So we want to say for I in range, length of the Senate, we're going to say if Senate I is equal to R, well, then we want to push you in the R queue, don't we? So we want to say R dot append I, else D dot append I, Fantastic. So now we've populated our 2 decks. The next thing we can do is say, while there are elements in DNR, whilst there are elements in DNR, let's get the values. So let's say rval is going to be equal to the value from the R queue. So we're going to say r.pop left, and then we can do the same for the dval. So let's say d.pop left. And if rval is less than the dval, well, we can say, what do we want to do here? Well, we want to add back to our queue. We're going to add back to our queue the R value, right? So we're going to say R value, but we also want to add the length of the Senate as an offset. Otherwise, we want to do the same for the dia. Okay, so now that's our logic, our main logic done. So this while loop will stop when either the D or RQ is empty. And then we can say return radiant if R, else dire, or is it the dire? Or, no, just dire. So yeah, let's actually submit this code. And there is a chance we've done something wrong here. Let me look through the code because it's taken quite a while to pass all the test cases. Okay. Oh, no, that's my bad. It did pass all test cases. That's just Leetcode being slow, and we have quite an optimal solution for this problem. So in terms of time complexity, for this problem, we're looking at a big O of n for time. This is linear time complexity. And for space complexity, it's also going to be big O of n because we are, converting this center string into a list, and then we also do have 2 decks as well. So I hope this problem made sense, guys. It's a bit confusing to wrap your head around, and I think that really just comes from the confusing description. But once you extract the key information and what the problem is actually asking from us, instead of focusing on the semantics of the problem description itself, coming up with a solution is a lot easier. But again, it is hard to come up with. It'd take me a while, and I would probably recommend, not beating yourself up, if that was you as well, because definitely was me, having to look up how, the best and most optimal way to solve this problem. And I think there are other ways as well. You can use stacks as well. You can use a linked list. That would help with the whole cyclic, thing that we're doing. But yeah, this is one of the solutions which I think is easy enough to come up with and also easy enough to understand. So I hope this video made sense, guys, and I'll catch you in the next one.